The objective of this lab was to start from observations of the spring mass system in the following video, and from these observations predict the motion of a mass attached to a spring oscillating while swinging in an arc. Additionally, we aim to analyze the changes in potential and kinetic energies within our system through the energy principle. To do so, I analyzed the observed motion in Tracker and then used Newton's second law and the energy principle as the fundamental principles to build a model in Python, which produced graphs of the XY position data and the energies contributing to the total change in energy. The result of this lab was a model which satisfied the energy principle and accurately modeled the motion of the spring and mass. For this lab, we took the weight, spring, and the earth to be our system. Because of this, we take the change in energy of the system to be equal to the change in gravitational potential energy, spring potential energy, and kinetic energy of the mass. By the energy principle, we know that delta E is equal to all of the energy transfers from the surroundings into the system. So because we have nothing in our surroundings transferring energy into the system, delta E is equal to 0. This will be key when determining whether or not our model satisfies the energy principle. Additionally, we know the values of the gravitational potential energy, spring potential energy, and kinetic energy seen here. We will use these values and the energy principle in our model to observe how delta UG, delta US, and delta K change as the spring oscillates and verify that their sum is 0. We also utilize Newton's second law in the form seen here and the position update formula to iteratively predict the motion of the mass spring system, similarly to how we did in labs 1 and 2. The following data was used to initialize our model. Given to us was the mass of the weight, the calibration length, and the time step between frames. These values were inputted into Tracker, and then the mass attached to the spring's motion was tracked to produce the XY position data. This was saved to a CSV, which is read in by our code here, and used to display the motion of the mass in the same window as the model, and also to produce graphs of the X and Y motion data against the predicted motion data. The initial velocity was calculated from the XY position data, but because it was difficult to choose the exact frame Dr. Greco released the weight, this value caused the model to over-predict the motion. I adjusted the value so that the model fit the observed motion, the value being that seen here. The spring constant was calculated by dividing 4 pi times the mass of the object by the oscillation period. I used the Y oscillation period to find the spring stiffness because its formula contains the spring stiffness value. I did so by averaging the length of the 5 oscillations seen in the bottom graph. The X oscillations can be found by taking the square root of the stretched spring length over G and multiplying it by 2 pi. This period is different from the Y oscillation period by 0.115 seconds. We see that these values are different because the X oscillation is related to L over G and the Y oscillations are related to M over Ks. Lastly, the relaxed spring length was calculated by subtracting mass times G over K from the stretched calibration length of 0.7. These values were then implemented into the code as variables. To predict the motion of the mass, we must implement Newton's second law into our code. Newton's second law tells us that the net force is equal to the sum of all the forces acting on the mass, here the spring force and the gravitational force. They are defined here in the code and then summed together as the value of F net. This value of F net is used in updating the mass's velocity, done by using Newton's second law in the form Bf equals Vi plus F net over m delta t. The mass's position is then updated from the new velocity. Implementing the energy principle into our code required initially defining UG, US, and K from the formulas discussed on this slide. Each individual value must then be updated within the while loop, so delta UG, delta US, and delta K could be calculated. We first set the initial value of K, UG, and US. We then update K with the ball's new speed and calculate delta K by subtracting the new value of K from the initial value. Similarly, UG is updated with the ball's new position, and K is updated with the spring's new stretch. Delta US and delta K are then calculated in the same manner as delta UG. Running our completed code, we see that the mass, the blue ball, very closely follows the observed motion of the actual mass, the red ball. The black arrow representing the gravitational force points down from the mass and does not change in magnitude as expected. The blue arrow, showing the spring force, points away from the mass along the spring and gets shorter as the spring compresses and longer as the spring stretches. As the spring never reaches its relaxed length, the blue arrow is always visible. The observations all check out with our knowledge of the spring force and gravitational forces. Looking at the graphs of the X and Y position data, we see that they are both a very close match for the observed X and Y positions, with the oscillations matching almost perfectly in size and shape. The exposition data slightly overpredicts the motion, with the overpredictions getting larger with time. This could be due to a slight miscalculation in one of the variables, or the possible effects of drag, which was not taken into account. Looking at the graph of the changes in energy, we see that the green line, delta UG, oscillates opposite and equally to the red line, delta UG, which makes sense because US is larger when the spring stretch is larger and the mass close to the Earth, and UG is larger when the mass has a larger Y position value, meaning it is further from the Earth. We see that the kinetic energy in blue oscillates twice as fast and loses amplitude as time goes on. Most importantly, we see that delta E in yellow remains at zero the entire time, thus the energy principle is satisfied. In conclusion, by using Newton's second law and observations of motion, we were able to create a model which accurately predicted the motion of a mass swinging on a spring and satisfied the energy principle.